Hi, I'm Professor Simmons. This is just a quick reference video about uh, our static friction lab. So we're just going to go through some of the basics on friction, review that information, um, as well as uh, give you some details on how the experiment works, and then give you a little bit, a few notes of things to help the experiment go smoothly. So, um, so to start with, friction. Uh, the main uh, fundamental mathematical relationship that we're going to use with regards to friction is this observation that the force of friction is proportional to the normal force. Um, and I would emphasize this is an empirical relationship. It's not based on some fundamental physics or anything. And kind of the cartoon that we often have in mind with this is we have like, the box on a table or something, and you push on it with some force. If we draw in our forces, of course, we have the object's weight pushing down on the table, and then the normal force will be pushing back up on the box. And when you try and move that object, there is going to be a resulting force of friction that's given by this mu times the normal force. And I should say this is the Greek letter mu. Looks kind of like a U with a little extra bit on the front. And this comes in basically two flavors. So there is mu S for static. And think of this as basically not sliding. And then the other flavor is mu K for kinetic. And I think of this as sliding friction. And an example that I think is useful to keep in mind is to distinguish these is thinking about driving. So if you're driving and suppose you're going too fast or something and you start to skid, you've transitioned from static friction, where your tire is not sliding relative to the roadway, although it's moving, it's rolling, it's not sliding, to kinetic friction when you start to skid, in which case the tire is sliding relative to the surface of the road. And you know that that's dangerous, right, when you start to slide? Well, we can think of that from a friction standpoint because the kinetic friction is always less than the static friction. Okay. Once an object starts to move, to slide, the actual amount of friction decreases. And this is discussed in your textbook. Um, um, so we're not going to be looking at both kinds of friction for lab. We're just going to be looking at static friction. And the system that we're going to be looking at is the inclined plane. And it's nice because this is such a kind of ubiquitous system that's just appears so many places that it's really nice to have another excuse to investigate it. And so how that system works, you have an object, a box or something that's on a ramp, it's on an inclined plane. How do we approach this? Well, let's draw in our forces. We're going to have the force of gravity pointing down. We're going to have the normal force perpendicular to the surface. Um, And then we would break this, the sort of strategy that we've been using to make this problem easier to investigate is to break this into x and y, where our coordinate system is oriented along the incline. And this is helpful because if we don't do this, then we have the object accelerating in two directions at once. But if we do this, we can limit the acceleration to just our x direction, and it makes it easier to break down. So, but in order to do that, we have to decompose our force of gravity into x and y components in this coordinate system. So, and recall when we do that, the one along the ramp is mg sine theta, and the one perpendicular to the ramp is mg cosine theta. And then the one ingredient that we're going to add, and let me just put this in a different color just so it kind of pops, is the force of friction. So the force of friction, assuming this thing is sliding down, the force of friction is going to oppose that. And so it would be up along the ramp. In other words, in the negative x direction. Okay. So this is nice because it gives us a chance to review the system. So we have our forces drawn in. What would we do next? Let's look at the forces in x and y. So y is simpler because we're not accelerating in y. So when we go to sum the forces, what do we have? We have the normal force. That's bugging me. This is tilted. We have the normal force in the positive y direction. We're going to have mg cosine theta that's pointing down. And this would sum, according to Newton's second law, to the acceleration in the y direction. But that, of course, is 0. We're constrained to be resting on the surface. So this will sum to 0. And this gives us a relationship that tells us what the normal force is, mg cosine theta. Okay. Now, if we go and sum the forces in x, what are we going to have? Well, we'll have mg sine theta. Now notice it's going down the ramp, but the way that we have our coordinate system, that is the positive x direction. So this is positive. We're going to have minus the force of friction. And then, of course, this is going to equal the mass times the acceleration in x. And we will probably just drop the x here because we know this is the only acceleration that we're concerned with. So now we can put in what we know about this, because recall we just talking about the fact that the force of friction is mu times the normal force. We now know what the normal force is, so we can put these ingredients in here. G sine theta minus mu times mg cosine theta is going to equal the mass times the acceleration. Now, one detail. For lab, we're not talking about the case where it's moving. We're just talking about the case where it's stationary. So that will be mu s for static friction. Another thing to notice here, m, the mass of the object, is appearing in all three terms here, so that we can divide by m and cancel that. And then we're left with an expression for the acceleration. The acceleration is going to be g sine theta minus mu times g cosine theta. And so if we hadn't introduced friction yet, what we have now should be consistent with the frictionless case. So how do we do that? We could, for example, set mu s to 0, i.e. there's no friction, and then acceleration becomes g sine theta. And that's our familiar expression for the acceleration of an object on a frictionless ramp. So that agrees. We've just added a piece here. And then what we want to do to get at measuring friction is we want to find mu s. So what we can do is consider that as a function of theta, you tilt this thing up steeper and steeper and steeper. Eventually, it's going to start to slide. But until that point, the acceleration is 0. So in other words, you can solve this for acceleration equal to 0 and solve for mu s. So if we do that, just write it again here, just for. So we could, add this over, divide. Notice g appears in both of these terms. Divide by the cosine. And we come up with this really concise relationship that mu s is tangent of theta. And I'm going to call this theta max to mean this is the maximum angle before the object begins to slide. Okay? So this is basically the main, physics theory idea that underlies the lab. So what we're going to do So that's the system that we're looking at, is this inclined plane. And what we're going to do then is we're going to use FiveFox. If you don't already have it, get it at fivefox.org. And there's a link in the document about this. You're going to use Tools, under Tools. Go to Inclination. And go to Plane. Okay. So we're going to use that to measure theta max. And then if you have theta, you can get mu s. So basically how this works is you're going to the technology that this operates on is your phone has, oh my gosh, I can't draw a phone. Your phone has accelerometers in it in 3 dimensions. And the force of gravity is always pointing down. And the phone can detect which direction, which accelerometer, or which combination of accelerometers that is pointing along. And as a result, it can tell if you've changed the orientation of your phone. So this is the kind of thing that's used to assess, like if you're watching watching something and you rotate your phone, you know how the video will also rotate. So that's the technology in the phone that we're going to take advantage of. But we're going to make use of this to detect the angle. So if you have the phone flat, so if you're playing with it, if you have it in front of you and you're looking at it, and if you have it flat on the table, that'll correspond to theta equals 0. Or here, let me change back to black here. Okay. And then what you're going to do, and I can try and draw this, but if you tilt, if you tilt your phone, those accelerometers are still, they're pegged to the phone, but the force of gravity is always going to be pointing down. So it'll be able to tell you the angle that it's tilted at. And it doesn't actually matter how the phone is oriented, like if you rotate it around, because we're using this plane setting. Okay, so what I would recommend is to, take your phone, go to the inclination, the plane option, and play around with it and get a feel for the fact that it can measure the angle. So what we're going to do is, and it's probably easier for me to just show you this than try and draw it, because my powers of drawing are pretty meager here. But you're going to take an object, something flat, like a clipboard or a cutting board or a book, and take your phone. And so when it's flat, it's going to measure theta equals 0. And then as you tilt it, when it starts to slide, that's your theta max. So you can do this, tilt it. When it starts to slide, that's your theta max. So you can do this for the phone itself. And then you can also do this for another object. So, and to do it for another object, you can just hold the phone and then, like use your mouse, or I'll just use this mouse as an example. Now, when you tilt it, you'd monitor the angle on FiveFox, and then when the other object starts to move, that would be theta max. So you can just hold the phone, it doesn't have to move, and then monitor with it when the object starts to slide, and that's the theta max for that object. Go back to our whiteboard here. So what the data is going to look like is as a function of time. So when you record, it's going to measure this as a function of time. It's going to tell you theta, and kind of qualitatively, what it looks like is it goes up until it starts to slide, and then you can stop, and then it goes up until it starts to slide, and then you can go back to it being flat. And then you can do this, a bunch of times. And the thing that we're trying to find is theta max. And so you can see you can take all at once. You can take like 10 measurements in like less than a minute. It's really easy to take the data. You can just keep it all as one sequence. And then, like I said, if you know theta, then you can get mu s, because you know that tangent theta is equal to mu s. So in other words, if you take, the inverse tangent of the angle that you measure, or sorry, if you just take not the inverse tangent, just the tangent of the angle that you measure, then that'll give you mu s. Okay, so, and what I would recommend is, you can do this with the phone itself to kind of get the feel for it. And then you want to kind of design a comparison experiment. Where you use the phone to measure theta, but you look at some difference. So you could look at a difference in different objects, or you could look at different surfaces for the same object. You can kind of choose what you want to compare, because it's all going to be dependent on what you have at home, right? So I put a list of some potential objects that you can mess with just to give you some ideas, but really, see what you can come up with. It's interesting to you could test, for example, like a non-stick pan, like that's supposed to be a low friction surface, right? You could test that with an object and see and compare that to, a book or something. Or you could test, a really simple one would be to compare a phone with and without its case. So a lot of times a phone case has, it's got like kind of a rubberized case on the outside, and you could see if investigating what the coefficient of friction, what coefficient you get for that, is kind of what you would expect based on it being a rubberized case, and if that kind of makes sense. So yeah, I would do at least a couple data sets where you can see a comparison. Um, so that's kind of the lab in a nutshell. Let me give you a couple notes just to make things go easier. So one is to get data off of FiveFox, you have different options. Uh, you can export directly to Excel as an Excel file. You can do this like via email, for example. Another thing you can do is you can create a direct connection. So if your phone and your computer are on the same Wi-Fi, you can connect them together, and there's a link in the lab document about that if you want to do it that way. Then you don't have to download it, and you can actually turn the experiment on the phone on and off from your computer, which is kind of cool because you can have the phone, oriented somewhere where it's positioned somewhere where it's inconvenient to mess with it, but you can still get the data off of it. And then another way is that you can actually just inspect the data directly on the phone. Let me put it to you this way: just in the app, and that can be convenient when you have not very many data points. You can see how if you had to, so we're only working with like 10 data points or so at least, and that's pretty. It works well enough to do that. If you had tons of data points, it wouldn't be as convenient. So that's one note. Let's see, what other notes? So another note that I wanted to mention is just for stats purposes. So I think what you'll want to report is you're going to have this list of theta maxes, right? I think the easiest way to kind of analyze this is to convert those into mu s. And then once you have the mu s list, do your statistics where, just for completeness here, what you want is the average. And I'll just tell you what the I think you messed with these in one of your other labs. But part of why, just for, and just for completeness, then to connect this with your other lab. So these are the definitions for these, but in practice you would never like calculate these by hand. So you would do this in Excel or MATLAB if you'd rather use MATLAB. And in Excel you can hunt around, but there's different functions. It seems to be stdev.s is the one you want. And then in MATLAB, it's std. And just the one detail that I wanted to mention with this is that the standard deviation. So it sounded talking to students like most were familiar with standard deviation, but what we're going to use to actually report as our error is the standard deviation of the mean, which is you take the standard deviation and divide by the square root of the number of measurements that you take. Okay. So in other words, just for consistency, your measurement would look like the average value of mu plus or minus this delta mu, where the delta mu is given by the standard deviation over root n. So this is just sort of a statistical a detail, and I suspect that you've messed with this in your other, in another lab, but just to have this as sort of an appendix, a note for doing this lab as well. So you can do that, like I said, really simply in Excel, or if you prefer MATLAB, you can do it in MATLAB, or if you have some other environment that you'd rather do it in, you can compute those things. And then this would be the stuff that you would report out. And then in terms of actually reporting the data, you could make a chart or plot or something like that. Whatever is most efficiently and most really gets your point across. So that's a couple notes to hopefully help the process of doing the lab go smoothly. And then let's see. So we talked about what friction is. We're looking at it in the context of the inclined plane system. We talked about how we're going to actually collect the data in FiveFox. You can look at the phone itself, and then once you kind of get a feel for it, design, some system to look at. There's some ideas in the lab document, but really, do what you think would be interesting. And then a few notes about, actually calculating from your series of data points, the statistics, finding the average for mu, and then finding the error. We're going to use the standard deviation of the mean for that, like we did in our other labs. And yeah, so I hope that this little reference helps you with this lab.